Good morning, dear students. Today we are going to discuss about the numerical problem of flywheel. We have already discussed the two numerical problems in the previous lecture. In this lecture, we have to solve numerical number third for related to the flywheel. So this is the problem third. A shaft fitted with the flywheel rotates at 250 rpm. That means capital N is equals to 250 rpm, and the torque varies in the cyclic manner over a period of 3 revolutions. That means one revolution is completed in 2 pi. That means theta is equals to 6 pi. And the torque rises from 750 newton meter to 3000 newton meter uniformly during half revolution. This is given for the drawing a turning movement diagram, and determine the power required to drive the machine, and also percentage fluctuation in speed. That means we have to calculate the power and CS, a percentage fluctuation in speed, and also given the mass of the flywheel and radius of gyration of the flywheel. So now we'll start the solution. Now here the given data n is equals to 250, as I have already told, and omega is equals to 2 pi n upon 60, that equals to 26.2 radian per second, and mass of the flywheel is equals to 500 kg, and radius of gyration is 600 mm, that means 0.6 meter. Now we have to draw the turning movement diagram on the basis of data given in the question. And this is the vertical ordinate and this is the horizontal ordinate, and vertical ordinate represents the turning movement and horizontal ordinate represent the crank angle. And the maximum value of the turning moment is given 3000 newton meter, and the turning moment diagram start from 750, and the value of crank angle is given up to the 6 pi. That means 3 revolutions. So one revolution is completed in 2 pi and half revolution is completed in pi, and this is the total 3 revolutions, that is 6 pi. And the torque rises from here. Next the question said that the torque rises from 750 newton meter to 3000 newton meter uniformly for half revolution. Here you can see that it rises 750 to 3000, and remains constant for following one revolution. This is the constant for following one revolution, and it falls from 3000 newton meter to 750 newton meter for next half revolution, and constant for following one revolution, and after that the cycle repeat the cycle thereafter. And here you can see that this is the turning movement diagram. So we have to calculate the work done per cycle. So we know that the work done per cycle is equals to area under this curve. So we have to calculate the area of this total curve, but it is very difficult to calculate the area in this situation. So we have to divide this total area into number of areas. So first of all, we know the points of different point on the turning movement: A, B, C, D, E, F. And now I divide it into two areas, 1 and 2. And now the second area is also divided into this one: triangles, rectangle, and triangle. Now here you can see that this is the one rectangle, the second triangle, third rectangle, and fourth triangle. Now we can calculate the easily the total area on the basis of this rectangle and triangles. All we have to calculate the separate areas of these rectangles and triangles and add all the areas, so that we will have the values of total area under the curve. So these are the area number 1, 2, 3, and 4. So now we'll start calculating the areas. So we know that the work done per cycle, that is equals to area of the figure, total figure, and the area of one rectangle, the triangle, rectangle, and triangle. And we have already know about the values of the sides of rectangle and triangles. So we put all the values, and we have the value of work done per cycle, that is equals to 11250 pi. And we also know that the work done per cycle is equals to T mean into theta. We have already discussed in the previous lecture. The T mean into theta. Here we can see that the theta is equals to 6 pi. Now the here T mean into theta, that is equals to 6 pi, and now the T value of the T mean is 1875 Newton meter. So this value is representing in the diagram. So this is the diagram. You can see here we have to represent the value of 1875, or we can say that the T mean. This is the mean resisting torque line, mean torque line. The area above the mean torque line represents the maximum fluctuation of energy delta A. So now we have to calculate the area of these triangle, triangle 1, triangle 2 and this rectangle. So first of all, we have to calculate the area of this rectangle. We can calculate the easily because we know that this side and value of this side, but we don't know the value of LM and value of NP. So we have to find out the first value of LM and NP by the similar triangles ABG and LBM, and also these two similar triangles HCD and NCP. These are the similar triangles. So we are using the similarity of these two triangles and we will get the value of LM and NP. You can see here. So now first of all we have we calculate the value of power or power required to drive the machine. The first answer T mean into omega. We have already calculated the value of omega, and now we put the value of omega here and the T mean value of T mean. Then we have the value power is equals to 49.125 kilowatt, and from the similar triangles ABG and BLM we have already discussed in the during the figure, and get the value of LM is equals to 0.5 pi and value of NP is equals to 0.5 pi. So these two values we have calculated for which is required for calculating the area of the triangles above the mean resisting torque line. So now from figure we find that the values Bm and Cn also. Since the area above the mean torque line represents the maximum fluctuation of energy, therefore maximum fluctuation of energy is equals to area of LBCP, that means total area, and this area is divided into three parts. We have already discussed during the figure. This is the triangle, and this one is a rectangle, and this one is also triangle. So we have already calculated the value of LM and NP in previous slide. So we put all the values in this equation and we get the value of delta E is equals to 8837 Newton meter. But we also know that delta E, maximum fluctuation of energy delta E, is equals to I omega square CS. I omega square CS is equals to 8837, or I, that means mass moment of inertia, I is equals to mk square. And we have to calculate the value of CS in this particular question. Maximum fluctuation of maximum fluctuation of speed in percentage. So we put all the values of m, k and omega, and after the solving this equation we have the value of CS, coefficient of fluctuation of speed. CS is equals to 0.071, or we can say that 7.1%. This is the answer. Thank you very much.